Okay. So yeah, as Emma pointed out already, Ingo is in Germany right now, so he asked me to take over for this time for him. And it's a pleasure to me to introduce Rana Ezzeddine. She's a postdoc working with Anna Frevel at MIT. And she received her PhD in stellar astrophysics from the University of Montpellier in France, and started focusing on accurate abundance determination in cool stars. And as a JINA postdoc, she's working on determining accurate abundances of many elements in metal-poor stars in the Milky Way and dwarf galaxies. Emma, can you mute your microphone? And yeah, today she will talk about non-LTE iron abundance, non-LTE iron abundance study of hypermetal-poor stars. And before she starts, please, everybody else, please mute your microphones and turn it only on if you have questions during the day. Okay, please, Rana.
Okay, thank you so much, Lena. Hi, everyone. Thank you so much for joining. I'm really happy to be giving this talk for JINA webinar. And so I will share my screen now with you and start with the talk. Okay, sorry, 1 second. So, okay. Can you see my screen? Okay, great. So I will be talking to you today about a non-LTE. So for those who don't know me, as Lena said, my name is Rana Ezzeddine. I'm a JINA-CEE postdoc fellow, and I work with Anna Frevel in MIT. And today I'll be talking to you about a non-LTE iron abundance study of ultra-metal poor stars. But first, I'm going to start by explaining briefly what is the significance of ultra-metal poor stars and why is it interesting for us to be studying them. And so I will try to get my pointer to work. Sorry, 1 second. Okay, there it is. Okay. So I hope you can see my pointer now. And so on a cosmic timeline, if we look at the cosmic timeline, it is believed that the very first stars were actually formed around 100 to 400 million years after the Big Bang. And there have been many speculations about the properties of these very first stars, how they were formed, what were their initial mass functions, what are their properties, and how did they die? Now, because it's believed that these stars are actually massive, and so the first supernovae that occurred after these stars were actually believed to occur shortly after the formation of the very first stars. And from that, we know that the second generation of stars that came after these first stars were formed 100 billion years after the Big Bang. Now, we believe that these stars are actually still around. We have many reasons to believe that. It is because in the last 2 decades, we have discovered many ultra-metal poor stars that have very few signatures of metals in their spectra. And so they should be formed very long time ago. Another thing is that we have detected thorium and uranium in the spectra of some of the R-process ultra-metal poor stars or extremely metal poor stars. And these elements are of very important cosmological significance because they decay over cosmologically relevant times, which have very long half-lives. And so from that, we know that these second generation of stars are actually still found today. And so there have been many hydrodynamical cosmological simulations over the past years that are trying to determine the properties of the first stars. And so basically, coupled with primordial gas chemistry, many scenarios have came over the last few years on what were the initial mass functions of these first stars. And so some of these studies have shown that the initial stars, the first stars, or population 3 stars, were very massive, up to 100 solar masses. However, because there were no metals at the time of their formation, it is believed that if they were as massive as 100 solar masses, then no further stars would actually form after them. And another study showed that when fragmentation in the molecular cloud is added to the simulations, for example, Krief et al., it is shown that these stars would be low in mass on the other hand. And so population 3 stars should live until today, which is not the case. And so one thing we know for sure is that these population 3 stars do not live anymore. Now, I am not an expert on hydrodynamical cosmological simulations, but I just mentioned this because I want to tell you from an observational point of view, how do we study the properties, or how can we study the properties of the first stars? And so basically this is done by comparing elemental abundance patterns of the generation 2 stars, or the population 2 stars that are believed to be the progenitors of the first stars, and comparing these elemental abundances to supernova model yields of the first stars. And since these models require masses, or require abundances as an input, we can infer masses from this. I will explain a little bit. And so from a chemical point of view, the supernova yield models, which finally give products of the progenitor masses and the explosion energies, depend on the patterns of the abundances, as I said. And so, for example, the light to iron elemental abundances, to the iron peak elemental abundances, signify what was the initial explosion energies of the first stars, and odd to even elemental abundance variations, as was studied by Nomoto et al., for example, also signify what drove, or what is the driven energy of these supernovae. And so, as an input, as the elemental abundances are important inputs, we have to look further into that. And so, for example, I will talk a little bit about a study that was done by Placaital et al. In 2015, where they compiled the 21 most iron metal poor, or iron poor stars known to date, and they compared their elemental abundance patterns, as you can see below, to supernova yields that were computed by Hager and Woosley. And for example, here in these 3 panels, I show the elemental abundance for elements up to 30, up to Z equal 30, which shows that indeed the masses of the progenitor stars, shown here in model mass, were actually larger than 20 solar masses, even reaching up to 40 solar masses for SMS J0313, which is the most iron poor star known to date. When looking on the full sample of stars, Placaital et al. Found indeed that most of the progenitor masses, of the progenitor POP3 stars, were massive between 20 to 60 solar masses. This was in agreement with previous studies that studied just individual stars. For example, Keller, who studied the J0313 star, the most metal or most iron poor star, and Tominaga. And this was also an agreement with theoretical expectations that were drawn by Abel et al. And Brom. However, in order to assert these results, we need more sample of stars that lie within this range of metallicities that are below 4 dex. Now, from all of this, you can see that in order for us to constrain the properties of the first stars, we need precise chemical abundances, and we need them to be very accurate, because any change in these values can really alter the models and alter what we deduce about the first stars. However, one prerequisite to any abundance analysis is knowing the stellar parameter of a star, which actually are put as input into the models. And so, for example, one of the main parameters that we need are the effective temperature of the star, the surface gravity, the metallicity, which is considered to be the total iron abundance of the star, and the microturbulent velocity. I will talk about these parameters in detail in a bit. Now, interestingly, we find, or spectroscopically, we can determine all of these parameters from only studying the iron elements. Iron is very interesting, and I will show why we can use this element to determine the properties of the star. So, in fact, iron is one of the most important elements in astronomy. It is used widely in many studies, and we can determine many, and we can infer many properties about the stars just by studying iron. For example, that makes it very interesting is that it is at the end product of nucleosynthesis in massive stars, as I'm sure that you all know. It is also the main product of type 1a supernovae, and this happens through the radioactive decay of nickel-56. Now, consequently, from these two conditions, iron is highly abundant in the universe. And because of that, we find a lot of iron spectral lines in most stellar spectra, even the extremely metal-poor ones. And so this makes it very interesting. Additionally, people who study chemical evolution will tell you, like Benoit Coté, that the iron abundance or the relative abundances of elements to iron are actually used to probe the chemical evolution of the galaxies. And so by studying the patterns of elemental abundances relative to iron, we can infer many information about this. And most recently, people, because iron is also a very important opacity donor inside the stellar atmospheres, because it is very abundant. And so it is used also to study the solar and stellar interior and to model them more. Especially now we have a problem with the modeling of the sun that has been shown in Bailey et al., where the iron opacities have actually been used to put constraints on the modeling of the stellar interior. And so all of these are great and very important. However, in our study, we use iron, as I said before, to determine the stellar or the atmospheric parameters of the star, mainly the temperature, the gravity, the microturbulent velocity, and the metallicity. And so how is this done? First of all, to determine the effective temperature of the star, we use iron 1 lines or neutral iron lines because they are very sensitive to the temperature of the star. And so by forcing, as you can see in the lower panel here and the difference between the upper and lower panel, when we force that the iron 1 abundances shown here in the black points, when we force these lines, abundances, to have no pattern as a function of excitation potential, which is the energy of the lower level of the absorption line, we can infer the effective temperature of the star. The surface gravity, on the other hand, is very dependent on the pressure inside the atmosphere of the star. And so this means that it requires that there's an ionization equilibrium between iron 1 neutral iron lines and firstly ionized iron lines, so iron 1 and iron 2. And here I show this in the star J1204, that by forcing the ionization equilibrium between iron neutral and firstly ionized iron lines, we can infer the gravity of the star. The third parameter from which we can use iron lines to determine is the microturbulent velocity. Now, this microturbulent velocity, I will just give you a small definition. It is basically used as a fudge factor in order to account for all the velocity fields that are happening inside the star. Now, this is used when we are using one-dimensional model atmospheres, because in this case, the atmosphere is considered to be hydrostatic and not hydrodynamic as is considered in the 3D case. And so in order to account for the velocity fields that are in the star, we use this microturbulent velocity parameter. And so how do we determine this from iron lines? We determine this by forcing a no trend between the iron lines abundances as a function of the line strengths. And so you can see here on the x-axis of these two panels is the log of the measured equivalent widths, or the reduced equivalent widths, which is divided by the wavelengths of the line. And so already we have determined 3 parameters using the iron line spectroscopically. The third one, which is a natural one that comes from all of these, is that the metallicity, which is considered, where iron is considered the proxy to the total metal content in the stars, is actually determined from the average of, or averaging all iron 1 and iron 2 lines in the star. And so this is how we determine the stellar parameters spectroscopically from technical details here of how we determine abundances, because it's very relevant. Let's hope it's the right physics, in order to compute a synthetic spectrum and then compare it to the observed spectrum. And when we have a fit, this is how we say, okay, this is the abundance of the star, and it should be done for all the elements. Now, in order to simplify this, most abundance analyses assume 2 very important assumptions. One of them is that they assume that the atmosphere is one-dimensional, and this simplifies a lot of the equations used. And the second assumption is that they assume that the star is in local thermodynamic equilibrium, which means that locally the star is almost closed. This means that we can treat it as a black body. And so the radiative transfer equation can be basically summarized by the Planck equation. Now, while these 2 conditions can be valid in a lot of stars, you can assume that they are not valid in many other stars. And so the deviation from LTE, or local thermodynamic equilibrium, is very severe in stars which have conditions where the radiation dominates over the collisions. This means that where the metals are very scarce, and for example, in extended atmospheres where not only metals, but most of the elements are very scarce as we go toward the outskirt of the atmosphere, the LTE conditions are not valid and they fail. Additionally, in decreasing iron abundance, or stars which are metal poor, we don't have a lot of metals, and so we don't have a lot of electron donors in these atmospheres. And so in this case, also the local, or the LTE condition, will not be valid and can produce many errors or large discrepancies, as we will show later, as I will show later in my talk. And so in this case, what can we do? What we need is we should use the non-LTE. Now, the word non-LTE is just a loose term, which means that it is not LTE. But what it really means is that we have to take into account everything that is happening in the star. And so we have to solve the radiative transfer equation and statistical equilibrium equations simultaneously to determine the populations of all the levels in the atom in the star, and from that we determine abundances. I'm not going to go into details here, but anyone who's interested to learn more about this or talk to me about this, you're welcome to do this after my talk. And so this brings me all to, again, to what I'm going to be talking about, or what is the main, why is the title of my talk, computing iron non-LTE abundances in ultrametal poor stars. Now, this is a work that is done in collaboration with Anna Fribels. It's in preparation, it's at its end stages, and will be on the archive very soon. And so basically what we did is that we studied a full non-LTE iron abundance study for all the ultrametal poor stars which have a metallicity or iron abundance lower than 4 dex. And for that, we use the non-LTE radiative transfer called multi, and we use 1D model atmospheres. We don't use 3D because this is now computationally not possible for us. But of course, in the future, it would be very interesting to look at that. And so let's talk a little bit about these ultrametal poor stars. One shortcoming of them is that ultrametal poor stars, even though they do have iron lines, but they actually have very few, okay? This is better than most elements, but still some of them don't have iron lines at all, especially most of them don't have ionized or iron 2 lines in their spectra. And so how can we determine their stellar parameters, as I explained before, using the ionization and ionization excitation equilibrium? We need both, we need iron 1 and iron 2. And so for that, we needed an extra method in order to determine the parameters when we don't have a lot of lines. And how we did this is that we computed a 4D space multidimensional chi-square fitting. What is this? Basically, it is just computing non-LTE models in a temperature or effective temperature, log G, metallicity, and microturbulent space, and then trying to fit the observed spectra or the observed equivalent widths to all the models that we have pre-computed in this grid. And then the best fit, and we do this multidimensionally, which means it's not a single simple chi-square fitting, because these parameters are all interdependent, and only fitting to one of them would be wrong. It will bias toward this parameter. And so once we have fit these and find the best parameters, we then go to the second step when possible and check for excitation and ionization equilibrium. When all of these conditions are valid, we say that this is the non-LTE parameters of the star. Now, in cases where we don't have any iron lines, for example, those at the very, very metal poor end, we actually use upper limits to determine the parameters of the stars. Now, this is the list of ultrametal poor stars that we studied. So we studied 20 of them. We exclude one, which is located, which has a metallicity of -4. This star was excluded from our study, G7761, because it is very rich in carbon bands like CH, CN, and C2, and this requires a special kind of analysis that was not really possible right now, but we are interested to look into the star later and study it by its own. But however, we do have a good sample from which we can infer many characteristics about, or we can analyze our stars with. And so I will start by comparing. So you can see in this table, we have the stars, we have the literature parameters, where I should tell you that most of these parameters were determined either via LTE or photometrically. And so on the right side of the table, you have the derived parameters, where we have the non-LTE determined effective temperature, log G, metallicity, and microturbulent velocity. And so to show you a little bit, or a first look into the results, you can see that the non-LTE effective temperatures actually deviate from the LTE ones up to 200 Kelvin sometimes. However, we do find very good agreement or small differences to the photometrically derived values, which is very interesting. However, the larger differences are when comparing to the spectroscopically derived parameters. And this can be, of course, expected because, as I showed you before, when we are determining them spectroscopically, we're using iron lines. And when two different methods are used, the values are going to be different. Also, the non-LTE effective temperatures are lower than those determined via LTE. Now, to look at the surface gravity, so you can see here with the fourth column on the left and the column on the right. So we have from 0.1 even up to 1 dex difference when determining the log G spectroscopically in non-LTE. The non-LTE log G is higher than that predicted or determined in LTE, and so this shows you that we can have very large differences in log G, and log G is very important to the any abundance. I mean, if we want to compute the elemental abundances starting from this can affect largely all the results that we get, and so this has to be taken into account and looked at carefully. Now to compare the iron metallicities, so the total iron abundance, you can see that as expected, we would have large differences. And these differences can reach up to 1 dex at the very low metal poor end. For example, for SMS's JO313, even though this is just an upper limit, we can have a 1 dex difference between both, but even for the rest of the stars. And these differences, so the non-LTE the non-LTE iron abundance is actually higher than the LTE, than what the LTE predicts, and the differences between both increase with increasing metallicity. Now let's look all of this through a plot. I know it's a lot of numbers, but it would be nice to look at them via a plot. And so here I show you the non-LTE corrections, which are defined simply as the difference between the non-LTE iron abundance and the LTE iron abundance. Now, the results or the stars in our sample are the ones shown in purple, yellow, and these are they vary with temperature. Now, we have 2 possible scenarios. If we want to fit these results, we have 2 possible scenarios. And this arises that the most iron poor star, the JO3136718, or the Keller star that was studied by Keller in 2014 and Bessel et al. In 2015, because we don't have any iron lines at all in this star, we have to use upper limits on some iron lines, and so the black star is the result we get when we use the resonance iron 1 line at 3859.911, and this line is actually a very strong one, but it's a resonant line, and so this will produce a 1 dex non-LTE correction or non-LTE difference as compared to the other result that we get here with the open black star that you can see. This one was computed by using different lines, which are not the resonant line, but also strong iron lines. And this produces around 0.7 dex difference. Now, in order to see which one is the more accurate value or which one to use or adopt, and from that we can actually we can see which fit would be better for our stars, we compare our results with a very recent study by Nordlander et al. Nordlander performed for the very first time a full 3D non-LTE study of this very metal poor star. And you can see that they have also 2 different non-LTE corrections. The triangle, which has the red circle around it, is the difference between the 1D non-LTE minus the 1D LTE study, as you can see in the legend. And the square, the black square, is a difference between a full 3D non-LTE study minus the 1D LTE. You can see that our black open star is actually in agreement with their full 3D minus 1D LTE study, and this shows that we would rather adopt this value and so in turn adopt this fit for our non-LTE corrections as a function of LTE. Now, why are we doing all this? Because we want to see if we can come up with a relation that can compute the non-LTE corrections for the stars as a function of LTE, not only for ultra-metal poor stars, which are below -4, but also for the more metal-rich ones. And so you can see here at the lower end of the graph, we performed, or we compared our results to what we would get for benchmark stars that have higher metallicities than the one we studied. So these 3 benchmark stars, G6412, HD140283, and HD84937, which I'm sure a lot of people know about, they have been very well studied in the literature. They have benchmark stellar parameters, which means that their parameters are almost independent of modeling, because people have actually used asteroseismic values to determine their parameters, and so we know them pretty well. And so what I did is that I computed non-LTE corrections for these stars and see if they fit with what we get. And so indeed they fit very nicely, but we did not only want to compare to our results, we wanted to compare to other results. That means that we don't want to be biased in our with our method for these stars. And so you can see that the crosses, the orange crosses, are the values determined by Marcy et al., which is a non-LTE study that was done also recently for these 3 metal poor stars. And you can see that our values agree greatly with theirs. And so this is very promising. This means that maybe we can use this relation to determine the non-LTE corrections for the stars with even higher metallicities than the ultra-metal poor. However, I would say that with caution, because even though this works nicely, this does not mean that we should just use this relation to compute the iron abundances. We should perform a full non-LTE analysis, as you saw, because the stellar parameters can also vary. And so what we need is more stars in this region of the metallicities. And once we do that, we can actually confirm if our relation is true or not. Now, let's look a little bit about why is it that we have these deviations from LTE. Now, LTE, of course, is a simple way to compute things. It's very fast. It takes a couple of seconds to determine the abundances. However, you can see that there are huge differences when the populations are computed. And so you can see in this plot, we have on the y-axis, we have departure coefficients, which are defined as the populations of the levels computed in non-LTE divided by those computed in LTE. And on the x-axis, we have the atmospheric depth that is parameterized by tau at 5,000 angstrom, or the optical depth of the atmosphere. And you see that it's mostly that iron 1 lines are the ones that are affected by deviations or departures from LTE, while iron 2 lines, you see them above, they are hardly affected. And this is because the iron 1 lines are the non-dominant species inside stellar atmospheres, which means that any change in the conditions inside the star will actually drive these lines very far and will affect them much. And so you can see that the deviations or the departures from LTE at the outskirts of the atmosphere where the lines are formed can reach up to 0.2. So the departure coefficients show that the non-LTE is actually deviates very largely from the LTE values. So this is just from a physical point of view. Now I will show you just how will these results affect the full look at these ultra-metal poor stars. So I will just show a little bit what happens when we put the LTE and the non-LTE results on isochron. Now, it should be careful because isochrons are very, very model dependent, and these models are actually based on LTE. And so even though it is mostly used to determine the parameters of the star, whenever spectroscopically or photometrically are not possible, you can see that it doesn't really work very much when we just compare them to non-LTE values. And so the blue points, the blue diamonds are the LTE values that have been computed from a 12 giga-year isochrone. And when we put the non-LTE values, which are the red diamonds, they will all shift toward higher metallicity. However, this really does not make much sense because these metallicities are higher. And so this is why I just wanted to show you this. This does not mean that it's correct, but also it means that we should be careful when we use isochrones to determine the stellar parameters of the star. And so I will just make a small summary about my talk. I hope that you have enjoyed it. And so when we study non-LTE iron abundances, or we have studied non-LTE iron abundances of 20 ultra-metal poor stars with the lowest iron abundances known to date, we have found that iron 1 line formation, when we are modeling these line formations and comparing them to observation, they suffer from deep departures from LTE. In LTE are underestimated up to 1 dex, which can largely affect the eventual determination of other elements in the stars. And the metallicity of the star, or the total iron abundance, is underestimated in LTE as compared to non-LTE, even to 1 dex. And it increases while we go toward the lower metallicities. We come up with a relation, or a possible relation, between the non-LTE corrections as compared to the LTE metallicities. Now, this may be applied, and we have tried to apply it for stars with higher metallicities. We find a good agreement, and however, we should be careful with this, because we need more sample of stars in this range of metallicities to test if it can be really applied. And all of these, what do they mean? They mean that these have consequences on the initial mass function of population 3 stars, which require as input chemical compositions. And so if we input chemical composition computed with LTE, we're going to find different results than when we do it with non-LTE. I personally have not done this, but I would welcome anyone who would like to investigate this, and it would be very interesting to look at what will be the consequences on this. And the big aim of my work would be to determine a full chemical analysis in non-LTE for as many elements as possible, and then compare them to a supernova model yield and see what difference is that we get from what we have now. And this is work in progress that I'm working on now. Thank you very much for listening.
Thank you, Rana.
Sure.
So if there are questions, can you please point this out in the chat, and so that I can collect the questions or address the people who want to ask the question? There's one. I have a question. Benoit, please.
Hi, do you hear me?
Yes, I do.
Yeah, very nice talk. I enjoyed that a lot.
Thank you.
As you mentioned, so the non-LTE correction changed a lot FE on H, the FE on H ratios, but also the stellar parameters by sometimes 1 dex. Yeah. I was wondering, with these new set of stellar parameters, will the abundance of the other element will change?
Yes, certainly. I mean, we already expect that, just, from a hunch, we would expect that, but indeed we will find large differences. Because another thing that the stellar parameters, they will change the formation of the lines. So when we are using a modeling technique, a radiative transfer code, the input stellar parameters will change how the formation of these lines are, right? They will change the synthetic spectrum that we then compare to the observed spectrum. And so we will expect that up to 200 200 Kelvin in temperature will definitely change the line formation, and so is expected to change the abundances of other stars. And this is what I'm working on right now, trying to see what is the effect on other elements.
Oh, that's nice. Good. Thank you very much.
So I think Sophia or Andrew has a question.
Sorry, that was me, and I actually didn't type it correctly. But I presume there's quite a bit of modeling uncertainty in determining the initial mass function in population 3 stars, and I'm curious if that modeling uncertainty is actually smaller than or larger than the uncertainties that you're talking about in replacing non-LTE atmospheres with LTE atmospheres.
So you're talking about the modeling of the supernova yields, is that it?
Yeah, because in order to get the initial mass function from the ultra metal poor star observations, I presume you have to connect this to real models of population 3 stars.
Absolutely, yes. So to be honest, I'm not at all an expert in that. And this is why I said at the end, I would really welcome anyone who, I have not done this myself. And
I'm certainly not an expert either. So.
Oh, yes. Okay. So, I mean, I assume that, of course, they assume some modeling assumptions in theirs. I don't know what they are exactly, but what I would be interested to see is what would be the effect of, what the non-LTE corrections to the parameters, how would that change the initial mass function of these? And so I would welcome anyone who would like to investigate that with me. I would be very happy to look into that, but I don't know how do they compare in terms of uncertainties.
Okay, thank you.
Sure.
Okay, I think Ian has a question as well.
Yeah. Hi.
Hi, Ian.
So my question is about the line-to-line scatter that you would predict using non-LTE. So are there iron 1 lines that show considerably less dependence, or is this species wide? And is there any way to get a sense of the line-to-line scatter among iron 1 lines and the differences that you would compute, right? So you've got sort of this average on that plot.
Yeah.
How much scatter is there for a given star on that plot?
Okay, so I have not shown this specifically here, but it is one thing that is for sure is that we definitely see less scatter in the non-LTE than in LTE. Now, if we want to take a sense of how this varies, for example, with excitation potential equivalent widths, this is not very possible. We can know the behavior of some of the lines. So if you know that at 0 or at very low excitation potential, we have these iron 1 lines that are higher than the equilibrium most of the time. And this is because of the 3D analysis. So, I mean, this is because we assume 1D model atmospheres because these are affected mostly. However, in terms of other lines, it's not possible simply because the formation of the lines happens in different parts of the atmosphere, right? And so this can be affected by many things. And so when we do a full non-LTE analysis, we are computing the populations that we are including all the contribution from all different levels in the atom. And so just finding a relation how this varies as a function of excitation potential and how it's affected non-LTE is not very possible. And this is why I say be careful of using just a relation to non-LTE corrections. I mean, it's great, but it's better to perform a full non-LTE analysis because we find that some differences can be found.
Sure. Thanks.
Yeah.
Dwayne?
Yes. So my question is there a systematic shift with the actual abundances measured? So obviously there's differences between the abundances you showed for iron, for instance, but would you expect that as well across all the other elements so that there's the overall abundance measured is either, say, more or less between LTE and LTE? So I cannot predict that because some elements would actually show a negative abundance correction, non-LTE abundance correction as compared to a positive. For example, magnesium would show a negative abundance correction, and this all depends on what is the abundance of how abundant are these elements inside the atmosphere. And so, for example, why is iron 1 lines more affected by non-LTE than iron 2? It's because they are the non-dominant species, and so they are
affected more. And for magnesium, we have a different kind of scenario. And so we cannot really predict how this will, if it's systematic, if it will shift it positively or negatively. And so each element has to be looked at separately. Unfortunately, we cannot really predict that.
Gotcha. Thanks.
Yeah.
So Hendrik also has a question.
Yeah, I was wondering about the validation. How do you know the new abundances are now finally right? And I think you said you compared it full 3D models. And I was wondering, I think there's some questions about those models in terms of the solar abundances, and because you have this disagreement with geoseismology data.
Yeah.
So is there a way, can you apply your approach to the sun, or is there some other way to do that?
Yes, absolutely. So the reason that we believe there was much differences in the solar, even when using full 3D. First of all, I have to say that there has never been a full 3D analysis of the sun. I know that some people are now working on this. This is because it's computationally, it takes a lot of time. However, one thing about non-LTE that I did not go or dive into it is that there are a lot of uncertainties in the atomic data. And most of these atomic data are, for example, hydrogen collisions that I've talked about before. Now, hydrogen collisions, they are not computed for iron, they have not been computed quantum mechanically, which is what we require. And so before they were using not only hydrogen collisions, but even electron collisions. And so people have been using approximations, classical approximations. And this is why there was really big problems in the modeling of the sun before. But now we are working on some new collisional data, some of them that I've worked on during my PhD, and this would be very interesting to look into these stars where there were problems and see if indeed the collisional data were the ones that were causing these problems. And so it is now looking promising, I can tell you, for the near future that a full non-LTE 3D analysis would be done for the sun with really good quantum mechanical data for collisions.
Okay.
I have kind of my question's similar, but are there stars where, we know these parameters like log G, T effective, very well, and could you try, would it not be possible to apply your method to calculate that and then compare with the ones we know well, or is that just, we're not in that situation?
Yes, of course, there are stars with well-known parameters like the benchmark stars, but sorry, I don't understand your question. So what should we do with these ones?
Well, I mean, could you use this non-LTE method to calculate log G and compare to the very well-known value? Has that been done? Did I miss it, or
Oh, yes. No, definitely. I mean, so for example, accurate models or accurate stellar parameters that are modeled independent, let's say, are the ones that we compute either from parallaxes, for example, from what Hipparcos gives us, or, for example, the ones from Gaia that we are now waiting for eagerly. And, or, for example, we have also asteroseismic gravities that have been shown to do well and compared to these parallaxes. However, for these ultra-metal poor stars, we don't have these measurements, unfortunately. And so people have always been either using photometric methods to determine these, and in case we have some iron lines, people have been using spectroscopic. And so eventually we would hope that we have more methods to determine these parameters and then compare. But what I can tell you is that these comparisons to non-LTE have been done for higher metallicity stars where we have these parallaxes and these values. And indeed, it has been shown that the non-LTE gravities agree very well with the Hipparcos values. For example, I refer you to studies by Frederick Tevnai, 1999. It's somehow old. There's Creevy in 2013, and there are others as well who show these agreements. So it's promising.
Okay, yeah, that's what I was wondering. In those studies, do they also say, do they show this is how LTE does and this is how non-LTE does, or is it only looking?
Yes, absolutely. I mean, you already can see the difference between LTE and non-LTE, and this is expected, but then they compare to the parallax values and they find that the non-LTE values agree more with the parallax values than the LTE.
Okay, that's excellent.
More questions? Anybody? Okay, if that's not the case, then thanks for zooming in, and let's thank Rana again for this very interesting talk.
Thank you. Thank you. you.